Now that we have the basic idea of how to write a proof figured out, we're going to take a little bit of time to step aside and to be able to evaluate proofs. So instead of stating the result for this first one and then proving it, I'm going to give you a proof, and we're going to look at the proof and see if we can decide what the statement was that they were trying to prove. So what was the actual result? So here's the example. We have a proof where we're going to assume n is an odd integer, then n equals 2k plus 1 for some integer k, and then we've got some arithmetic, and we come to the conclusion since 3k minus 1 is an integer, 3n minus 5 is an integer. And we're given 4 choices of what the result may be. But without those choices even, we can figure out what this is trying to prove. So remember, when we're proving statements, they're implications. Sometimes they're biconditionals, but there's at least an implication, an if and then. And we always assume the thing that's paired up with the if, and we prove the thing that comes with the then. So here we have, assume that n is an odd integer. So I know the statement I'm proving needs to say something like if n is an odd integer. Now I work off of that idea of n being an odd integer, and I use the definition to make 2k plus 1 be my n. And then I work through this arithmetic, and I start with the statement 3n minus 5, plugging in my odd n, and I find that I have 2 times 3k minus 1. And then I say 3k minus 1 is an integer, so then definition of even, I have 2 times an integer, so 3n minus 5 is even. My conclusion, and the thing that I've proven, I started with 3n minus 5, remember? And I got to the point where I could say that that was even. So that's the then. So I have if n is an odd integer, then 3n minus 5 is even. And if we look at the options, then we can see that option 2 is in fact exactly that. Now, that's a direct proof. We said that the contrapositive is actually logically equivalent, so this proof would also suffice for the contrapositive of that statement. The contrapositive would be if 3n minus 5 is odd, then n is even. And if we look at this, statement 4 is in fact the contrapositive. Now, if we take a look at the other options that they give us, say you were given options like this, you could very quickly rule out option 1. 3n minus 5 is an even integer is not actually something that we can prove. It's just a statement. It's an open statement, and it depends on the value of n that we plug in. Statement 3 says let n be an integer. If 3n minus 5 is an even integer, then n is an odd integer. Well, in this, we would assume, to prove this, we would assume that 3n minus 5 is even, or we would assume that n is even. We've done neither of those things, so 3 is not an option. So there's going to be other times when you're given the results and you're given a proof, and you have to be able to look at it with a critical eye and decide if what this result is actually proven by the proof given. So let's take a look at this one. We have x and y are integers of the same parity, then x minus y is even. Well, x and y being the same parity means they're both even or they're both odd. And that sets me up for a proof by cases. So in this, we come to that conclusion that they're both even or they're both odd, and we have a case for x and y are both even and x and y are both odd. This is a great setup for a proof. Well, then I look at it and I look at case 1. X and y are both even. Then it says let x equal 6 and y equal 2, which are both even. Then x minus y equals 4, which is even. Well, they've now proven that statement to be true in this one example, when x is 6 and y is 2, but I'm not convinced that it's true generally. So the statement as a whole is not actually proven in that case. And case 2 has a similar problem where they take the example of when x is 7 and y is 1, and they prove it for that one example that the difference is in fact even. So if I look at this, I can say, you know, this proof, it's not actually a proof of the result because it just uses an example for the cases and it doesn't prove them for a general or generic x and y. All right? So that's one example of how you might look at a proof with a critical eye and figure out whether it actually is a proof or not. So here's another example. We have m is an even integer and n is an odd integer. Then 3m plus 5n is odd. So let's take a look at the proof provided. We have m is an even integer and n is an odd integer. They make that assumption. That's great. That's the thing paired up with the if statement. Then m equals 2k and n equals 2k plus 1. That's the definition of even and the definition of odd. Therefore, 3m plus 5n equals, and they do some arithmetic. I don't see any errors in their arithmetic, and they arrive at the conclusion that 2 times 8k plus 2, which is an integer, plus 1 is the solution. So that means that 3m plus 5n is in fact odd. This proof might seem convincing, and it is in fact a little more convincing than the previous one. However, it's not actually a ton more convincing. Let's take a look at the definition of even and odd when we set it up with m equals 2k and n equals 2k plus 1. Since we've used the same variable k in each of those equations, what I really have is m is an even integer, and n is the odd integer that follows that even integer. So this only works for m and n that are neighbors. Instead, I could improve this by using a different variable for one of these. So I could say m equals 2k and n equals 2j plus 1, where j and k are both integers, and then this whole thing would work out and it would actually be a proof for the general case. This is a little bit harder to spot when this error occurs, but it's a really common error, just like the proof by example in the previous example that we did is also a common error. So as you're writing proofs, I encourage you to take a minute and to evaluate your own proofs. It's easiest to do this if you give yourself some time between the writing of the proof and the evaluation. Even better if you get to sleep between the two. So write the proof the next day, you get to evaluate your proof and see if you've actually proven the result. All right, so this is a great skill to have. Work on it. With practice, you'll get good at it. It's going to be great.